Well, this is a start, hopefully, at least 45 minutes or thereabouts. So, this presentation is going to be about looking at life through a slit, really looking at time through a slit. Sometimes this method is called slit scan photography. I got involved in this kind of a roundabout way by making my own photographic equipment. I made reflex housing, telephoto lenses, enlargers, and a whole bunch of other small items, even bellows and stereo camera once. And so I like to tinker with stuff. But the thing that interests me most after becoming a teacher at the Rochester Institute of Technology is high-speed photography, which inspired by Harold Edgerton from MIT and encouraged by my supervisor, Kenneth Hickman. I've worked in technical photography in particular in many aspects. So I worked for the US Congress on the examination of photographs of Harvey Oswald holding a gun. I worked with a criminal investigation of someone who claimed not to have owned a particular pair of shoes, and yet there was a photo of him wearing them. I did consulting work for NASA Glenn Research Center, Langley Research Center, DASK Corporation, Remington, and many others. I've been published in Popular Photography Camera Magazine, Digitalische Fotografie, or Digitalische Foto, I don't remember, Popular Mechanics, etc. Oh, there's Digitalische Foto. And some of my technical photographs have been exhibited in museums and galleries of various kinds, and also my attempts at art photography were exhibited in various locations. The people who inspired me most were George Silk from Life magazine, and also the others that kind of mimicked Silk to begin with. And you can see them there. Sam Brightman was an independent photographer. Bob Galbraith, an independent photography, as well Jerry Danzig and William Larson. Let's not forget a Hungarian newcomer to the field. He works in digital work, and his name is Adam Magyar, yes. But in the field of technical photography, high-speed photography, there are many important contributors to the field of detonics physics, explosions essentially, and some of these worked on the first atomic bomb that was created at Los Alamos Lab. So now let's take a look at some photographs. Here's a photographs by Neil Leifer, 3 of them. The 2 on the right are not really that great. They're sports photographs. The one on the left, however, could have been, or one could think that it was made with a regular camera, just panned as this diver was diving. But in fact, it could not have been. It had to be made with a special camera, and you'll see details of that as we go along. Heinz Boguslawski had a big spread in Stern magazine many years back. Jerry Danzig is a landscape photographer using circuit cameras. But my inspiration was George Silk. And this happened because I was doing kind of standard sports photography when I was in school. And my advisor told me that my photographs were very mundane, very uninspiring. And he asked that I come up with some more artistic photography. I saw the work of George Silk, and within a week I had dismantled the camera and mimicked the camera that he had, and made these photographs on the right. So things have changed for me. However, my interest in technical photography remains. So here are some of these photographs I made a la George Silk. Still sports photography, but in a much different light. Um, so are these art? I don't know. They were interesting. Uh, so I've stopped doing sports photography, but I'm still connected with this particular method that you'll see. I published in Popular Photography in 1971. I get a couple of pages in this magazine detailing my experiments. And Camera magazine in Switzerland, very high class magazine, had my photographs on the cover. Popular Photography magazine, when it had its first double page cover, used my photograph because it was long and that's what they needed. So, all right, now let's talk business. Slit scan photography. We'll start this conversation with this slide, just realizing that basically slit scan photography is focal plane shutter distortion. Well, so what is a focal plane shutter? Well, here on the left-hand side, you see a green box. That's a large format camera, and it has a slot in the shutter, and that moves across the film plane. Next to it is a leaf shutter. That is a shutter that is closed to begin with, and it opens up over time, and then it reverses itself and closes up. It's an interesting thing to think about because all of the image is exposed at once. So when the top is being exposed, so is the bottom. Side is being exposed, so is the other side. Not so with a focal plane shutter. You can see it sort of in action at the bottom. In a Nikon camera, the slot is at the top of its travel, and then on the right you can see at the bottom of its travel. You'll notice it has increased in size as it went down. And why did they do that? Well, because you need to keep the exposure time constant, and by increasing the slit size, you accomplish that. Well, then, besides these two, in this digital age, there is such a thing as a digital global shutter. I'm not going to spend too much time on that because I can't afford it. So let's just take a look at what happens when you photograph a moving object or moving object with the focal plane shutter. So here we have an image of a square and an object and a square and a circle. And they're standing still on the left-hand side. Whether you photograph those with the focal plane shutter or the leaf shutter, the effect is exactly the same. Still images. Now, when the object is moving, let's say as it says in the second slide there, or second part, with the leaf shutter, all you get is blur. Now, with a focal plane shutter, if the slot is moving in the opposite direction that the images are moving, in that case, you'll get compression because it takes less time for the images to cross the slot than if the images had been standing still. Now, the opposite happens when the slot is catching up to the images. In that case, you get stretching. Now, if the slot is moving perpendicular to the object, in that case, you get leaning to the left or right, as this illustration exemplifies. Now, there's one photographer who took advantage of this. He wasn't the only one, but the one who made a splash in the art world, and his name was Henry RT. French photographer used a large format camera like that green one that you saw earlier. And here you can see people in the background who obviously were not leaning like that, and the car with this elongated oval-shaped wheel. Now, how did this happen? Well, it happened because the slot was moving from the bottom to the top as the car was moving. Now, the photographer, if the photographer had moved the camera at the same speed as the image of the cars would have appeared, in that case, the wheel would have been nice and round. But he wasn't moving the camera fast enough. What about the people in the back? Well, they're obviously standing, and as the camera is being panned to keep up with the car, they're being left behind. So they end up to be tilted. This is known by everybody as focal plane shutter distortion. And it's been around for a long time. But it's most noticeable with large format cameras. And these days with iPhones or with phones. Now here's focal plane shutter kind of in a different illustration. So the vehicle is going to be moving from right to left. The camera is not panned fast enough. So by the time that the slot arrives to the top of the wheel has moved to the right. If the panning action of the camera is right, in that case, the wheels appear nice and round, but notice the markers in the background, they are tilted, just like in the Lartigue photograph. Now, if you can't pan the camera too quickly, in that case, you get leaning in the opposite direction. Note that the distance between wheels remains the same. That's because vertically, as it goes along, the distance between objects remains the same. So focal plane shutter distortion. Now, what can you do with this? Well, you can do a variety of things, but in a commercial world, here is a Derek Grage photograph from the 1980s for this album cover, and it was photographed by a moving slot in the camera. As the slot is moving down or up, either way, the door is opened. When it's in her middle, the slot is as wide or the door is as wide as it can get, and then she closes the door, and then it closes. So it's an interesting visual effect, easily attributed to focal plane shutter distortion. Now you may see this effect or similar effects when you make photographs with phone cameras. Some phone cameras, they have not a moving slot, but they have a scanning action to the making of the photograph. So if you change the subject rapidly during the making of the photograph, you end up with distortions like this. You know, obviously that bridge doesn't have the railings tilted like that, or on the street, the railings are not bent. You can also see it when you photograph airplanes, the prop planes. The props, if you make a picture of them, they'll end up distorted like this, depending on the direction of motion of the sensor that's scanning the image. You get various types of distortion. However, this is not new. People seem to have noticed it recently, but in the pre-digital age, we used to see this once in a while when you photographed an airplane. Whoops, like this. When you photographed an airplane, or when you're driving along and your windshield ends up in a strange shape. It's all due to focal plane shutter distortion. Now we exploited this effect to advantage in our class at my school to make some funny, interesting photographs. Just imagine all of these were not made all at one time. They were sequentially exposed through a slot that was moving from the top to the bottom, or bottom to the top, or side to side, as on the upper right. I'm sorry. So now let's deal with streak photography. Instead of moving the slit in front of a stationary film, how about if we move the film behind a stationary slit? So what does the situation look like? Well, like this. We'll forget about the fact that photography only works in a dark camera, but imagine if there was a lens and a box that it's in and so on. But in this system that we set up, we have a slot that the film is exposed through, and there's film that moves behind that slot. So as long as nothing arrives, no image arrives at that slot, regardless of what happens, the film just gets exposed evenly all the way from one end to the other. However, what happens if we put an image of something, such as maybe a fluorescent tube across that slot, such as this? Now, if this happens to be a fluorescent lamp and it's turned on all the time that the film is moving underneath, in that case, the part of the film that sees that lamp, that part of the lamp, exposes the film as long as it keeps moving. What's the result? Well, a line of density that extends from one end of the film to the other. But what if that lamp is not left on or not turned on all the time that the film is moving? So the film is moving, sees nothing, lamp is turned on, it sees some light, and later on the lamp is turned off, and then back to nothing. What do you think the result will be? Well, a line of brightness of something. And how do we interpret this? Well, the length of that line is an indication of the amount of time that lamp was turned on for. So the longer the line, the longer the time that is recorded on the film. If you know how fast the film is moving, in that case, you can make a quantitative analysis of this. So let's say that the film is moving at a centimeter a second, and you measure the film and you find that the length of that is 4 centimeters. Well, in that case, you can tell that the lamp was turned on for 4 seconds. It's not much of an information, but it's very valuable in some situations when you need timing information. You got to remember that the direction of motion of the film, or actually the film itself, is a time record, not a spatial record, not height or width. It's length of time. So what else can you do with a streak system like this? Well, you can make the image move. So it is at the bottom of the film at the beginning, and then it's higher, and then higher, and eventually it leaves the edge of the film. What do you think the record is going to look like? Well, if the motion is consistent, in that case, the result will be a diagonal line. That line will stand for the speed, and you can determine the speed of the object, or the image anyway, by the slope of that line. Or you can just measure the intersection at the top and the intersection at the bottom, measure the distance between those two. And if it happens to be 4 centimeters, you'd say, well, it took four seconds for this image to travel from the bottom of the film to the top of the film. If you know how wide the film is, then you can say that however wide the film is, that's how long, well, that's how fast, essentially, the image moved from one side of the film to the other. So for those of you photographically inclined, how wide is 35 millimeter film? Well, if you had to think about this for a while, in that case, let me clear up the situation. It's 35 millimeters wide. That's why it's called 35 millimeter film. So if it took 4 seconds for it to traverse the film, the image was traveling at 35 millimeters in 4 seconds. And what's that? Almost a millimeter a second. Anyway, what if the subject or the image accelerates or decelerates? Well, instead of a straight line, you'll get a curved line. The line on the left shows acceleration, and the one on the right shows deceleration. We have to just remember the fact that the horizontal distance in these images is time. Vertical distance is, in fact, the real dimension, like meters or centimeters or whatever. So what if we change the situation slightly? And now we have an image that vibrates up and down, as shown on this slide, and the film moves underneath. Well, in that case, if you thought, or if you determined that what you would get is a wave, in that case, I will agree with you. Now, this could be a sine wave, or it could be any other wave. This time, you can tell or determine from this result something else. You can determine the time that it took this subject to make one cycle. So from peak to peak, that's time. That's how long it took for this thing to move from bottom to top and top to bottom. That's pretty useful information in engineering and technical terms. So what about an actual application? Well, in my classroom, we launched model rockets. And on the left there, you can see the rocket sitting on its launch pad. And the engine has ignited, but it doesn't produce enough light or thrust to raise the rocket into space. But as time goes on, the engine gets hotter and hotter, and it starts to produce enough thrust to lift the rocket off the pad, and then it accelerates upwards and until it hits the ceiling in my classroom. It's interesting when the rockets come back to ground and students are scrambling to get out of its way. Anyway, it's a lot of fun. By the way, those horizontal lines that you see are not actually there in the original record. They're there just for information purposes, so you can tell something about how fast the rocket was traveling at a given time by looking at the slope of that line. Now, in a more complex situation, we did an experiment where we tried to determine the speed at which bullets travel. And that is not something that normally you would be able to do with a camera. However, with a streak photograph, it is possible, as you'll see. Here are my students setting up the experiment, and this is the camera that they will use. It's a rotating drum, and it can be made to, that drum can be made to rotate, and it rotates around 6,000 RPM. In any case, there's a slit just in front of the film, which is taped to the drum, and there's the lens there to put an image on the slit. So with this camera, by making a record of the flight path of a bullet, we're able to determine its speed. So in my classroom, this is what we did. Up in the red area, there's the students operating the camera. At the bottom, there's me firing the gun. The bullet travels across two wires that are strung in its flight path. Not exactly its flight path, but because otherwise we'd have to replace those wires every time, but we go close to it. And the result is the picture on the middle. So again, one of these bullets is traveling faster than the other. Now, what do you think is faster? The one with the steepest slope, and that would be the bottom one there. And in this case, although you would get double exposure when the drum makes more than one revolution, it doesn't often really matter because the two bullets would have to overlap in order for it to be hard to determine which is which. However, we also did an experiment with exploding wires. Well, what's an exploding wire? Well, you take an extension cord, you have two wires inside. You attach a very thin wire between the two, what you'd call electrodes, and you plug it into the wall. Well, this might destroy the electrical system of the building that you're in, However, uh, and also it makes a loud bang, and it makes light, and for some time. And you might want to see what the performance of that exploding wire is. Well, you put that on the slot of the camera, you rotate it, and eventually you end up with a streak photograph of the performance of that wire. Hopefully, you don't electrocute yourself. Just a joke. So I wouldn't try this at home, as I say. You can also make the situation be such that you arrange a bunch of crayons like this up across the slot of the camera, and you make them move up and down. I don't think there's any technical purpose to this, but maybe it's something that artists will appreciate, or things like this. Is this art? I don't know. Some people think so. Let's move on. Here's an experiment or a situation where we have a spring that's holding a lead weight, and that is made to bounce up and down. And the image of that weight is put onto the slit of the street camera. Here you see the spring in two different positions. That's just to show that at one point it's high and other times it's low. Just bear with me. We're going to use just one spring. And it'll be high at them sometimes, it'll be low at others. To get timing information, you put a little LED timing light, which is flashing 100 times a second. What do you get in a situation like this? Well, this is reminiscent of the very early reference to objects moving up and down on a slit, right? So here is the result. I picked up a couple of places at random. One where we're at the top of its travel, and one at the bottom of its travel on the far right. And then I enlarged the area just above where it's at the top of its travel. And there you'll see that the springs are compressed. The distance between them is less. Oh, no. More at the top than at the bottom, because at the bottom, oops, I think I'm wrong. So here is the result. I have picked up two places at random. Well, not exactly, but I picked up two places. And one of them is at the top of the travel of the spring, and the other is at the bottom. That allows us to determine how much time elapsed between peaks, and that is an indication of frequency. Now, if you look at the detail, you'll notice that when the spring is at the top of its travel, it's most very compressed. The distance between the little springs is small. However, when the spring has been stretched by that falling lead weight, in that case, the distance between the springs gets bigger. So you learn an awful lot about, or you can, if you're interested, by making streak photographs. Now, they don't look like anything that you'd actually seen, because you're looking at time itself. Very important in the technical field in particular. This was a camera that I had which makes the process of sweeping an image of a slit much quicker. This came out of a national laboratory as a surplus, and it weighs a ton, but it has a rotating mirror, in fact, and that wipes the image of the slit onto a curved track. In any case, what can we learn from the picture that this camera makes? Well, we'd like to determine the time between flashing a flash and then a slave flash, a slave that picks up light from the first one and triggers the second one. The time between the two has to be pretty short because we can't see it. But this camera can provide a record that looks like this. There are two traces there. One is the main flash. It's a little brighter than the slave flash, but notice that the peaks of the two are offset, and they're offset by a number that can be known by knowing how much a particular amount of film stands for in terms of time. This one was moving at 10 microseconds per centimeter. So we can measure the length of these traces in terms of centimeters, and we're measuring it in terms of microseconds. And so from there on, you can do a little bit more math and learn about that very brief time that it takes to go from one flash to another. Now, we're going to look at another application, strip photography. Remember I said we're going to talk about time. So let's change the situation. Instead of having an object just moving up along the slit, up and down, for example, let's move the image across the slit while the film moves behind it. Remember, recording time. So here's the setup. The camera, this black boxes, as we talked about. The film is standing still, the image is standing still, and in this case, nothing is happening. The film can't record anything. So what about if we change things? We'll make that square image move from left to right, while the film underneath is also moving left to right. The two, we have adjusted the speed of the two to match. How we did that, maybe we'll get onto it later. But somehow, magically, we do it. So if from this time, as you see on the slide, we let time run forward, eventually that square, the image of that square, is going to cross the slit. At that point, the slit will see that image. And then eventually, as that image crosses the rest of the slit, eventually it passes, and then you see nothing again. What about the image? Well, it took some time for that image to cross the slit. In the same amount of time, because the film was traveling just as fast as the image was, a length of film exactly equal to the length of the image is able to pass underneath. So what does the final record look like, and what's the result? Yeah. Essentially a perfect reproduction of that square object. What about if things are different, though? If we make the film move faster than the image? Well, in that case, in the amount of time it takes an image to cross the slit, a length of image in the length of time that it takes that image to go across the slit, a length of film exactly twice the length of the image is able to travel underneath. And the result, as you expected, is stretching by a factor of 2. Now, if the opposite happens, the image travels faster. In that case, in the time it takes the image to cross the film, only half as much film can go across, and the result is compression. Now, what happens if you make the image and the film move in the opposite direction? Think about this for a bit. It'll take some time for that image to go across the slit. Because the film is traveling at the same speed as the image speed, the time information will be the same, except that in this case, the head of the arrow is exposed first, just like it was before, but going in the opposite direction. So because the timing is the same, or the distance is the same, all you will get is a reversal of the image. The length of it will be the same as the original image. It'll be blurred a bit because there is motion between the film and the image, but aspect ratio wise, it'll be the same. Now, the most popular application, I'd say, of this kind of a system is photo finish photography. Everybody around the world wants to know who won a race, who came second, and so on. And they make photo finish photographs. Not that many people understand what these stand for. Some of you may. In any case, I will review it. So here's a photo finish camera, and it has a slit in the back. It has a lens to form an image of the horses on the track onto the slit of the camera, and some means for moving the film at some desired speed. The slit is lined up with a couple of posts on the track. The edge of those determines the finish line, but there's no actual line there. The line is inside, essentially it's the leading edge of the slit that's in the camera. So how does the camera operator, how does the system work? Well, at the beginning, the races stopped, but at the beginning, the races started, and the horses run around the track. And eventually, they start to get close to the finish area. At that point, the camera operator turns the camera on, and the camera starts to record what's in front of it, which is essentially just dirt. And so the dirt, because it's not moving anywhere, is just leaving horizontal streaks. But eventually, a horse's nose crosses the edge of that slit, and the film, dutifully records it. And the length, the horse is continues to travel and continues to be recorded as it travels. The image of the horse travels over the slit. Either during that time or at another time, a second nose appears, and the film records that nose and the rest of that horse as well. And then the third, fourth, and fifth, and so on. Horse do the same thing. And then once that's done, the photo finish camera operator snips out a short length of film and processes it and shows it to the judges within a minute. Now these days, these cameras, as you'll see later, have been replaced by digital versions, but they work essentially the same. So here is a photo finish photograph, and we can ponder about this for a bit. So this is a photo for place. That means it's a photo for second place. So horse number one is surely won the race. Horse number three came in second. Horse number five probably third. The question that I have for the audience here is, which horse do you think came in fourth? Horse number 10 or horse number 6? Well, or you could also choose, well, you can't tell from this photograph. If you said you cannot tell, I think you need to rethink things. If you pick number 6, you probably also need to rethink things. If you pick number 10, in that case, and even number 1, or everyone, I'll ask for you to tell me, where is the finish line? If you picked that white line that you see, in that case, you're right. However, you're wrong. Why? Because that white line was never on the track. It was added by the photography camera operator just to show you that a finish line, because you wanted to see one. The audience wants to see one, but there was none on the track. So where is the finish line? Well, the finish line is everywhere. An impertinent answer would be, you're looking at it. And you're looking at it on the right side and on the left side. We're looking at it all at one time. but that's all different times. So what about digital systems? Well, they're the same thing, except what they do is they have a linear array in the focal plane, and that is being scanned very quickly and then stacked, one scanner after the other. And they can do that, I think, about 1,000 times a second. So, but now there's no film involved, no chemicals to deal with, and so on. So that's a photo finished digital camera, which is what is available at most racetracks these days. So what, by summary, you might say, a photograph made by this system is not distorted, the images are not distorted, when the film and the image velocity can be made the same. So how do you make that? Well, maybe you know something about how fast the image velocities are when the subject velocity is known. I mean, you have the horses on the track, you know roughly how fast they're moving. The images are going to be moving slower than the horses themselves, and it's going to be affected by the optical magnification of the camera. So if you know how fast the subjects are moving, you can easily figure out how fast the images are moving. Once you know what the images are moving, then you can make the film velocity the same, and you don't get distortion. I'm getting a sore throat here. And another thing is photography and digital results also depend on proper exposure. How do you figure out what the proper exposure is for film cameras? Well, if you know how fast the film is moving, the width of the slit divided by the film speed is equal to the exposure time. And once you know that, you can determine aperture, etc., using a light meter. So what else can we do? Well, we can do something like this. But this time making a car move in front of the camera. Moving in front of the camera being in a car that is driven past these stationary vehicles. Now I'm going to show you just a couple of improvised simplified systems, starting with how to make a strip or street camera from a regular camera. And here's one situation. Notice that the back of this camera has a slit in it. And other than that, it has a motor to move the film. If you don't have a motor, in that case, you can install a slit and then move the film by simply rewinding the film with the shutter open. Now, we have found through extensive scientific research that number 2 pencils make the best levers to keep the film speed constant. And that's a joke too. So here's my first attempt at making a motorized strip camera. Here's a simplified version of that, and you can start to do strip photography of moving vehicles. So here they are in motion, but I also do stills, of course. If I can make, okay, here we go, such as these. And I can guarantee you that a regular camera could not do what is going to be shown right now. But what if you want to make you have a piston like this, and you want to photograph it all the way around so that you could see the defects and so on? Well, one way to do that would be to just take a bunch of photographs and then look at them sequentially. However, you could do something different. You can place the object on a turntable, make it rotate, place the center of rotation on the slit inside the camera, lock the camera up, wind all the film to one side with the lens cap on, and then use the rewind process to rewind the film. And you end up with a peripheral photograph. Some people call it rollout photograph, but it's a peripheral. It shows you all sides of the subject, however, at different times. And if you don't make the speeds match, you get distortion. However, it's still useful for a variety of things, such as when you have a pot which is being reassembled after falling into pieces. And when you put this in a turntable, rotate around, you can see all sides of this pot all at once, and you can count the pieces. Now they're going to be slightly distorted, but that's because you can't match speeds everywhere on that pot because it has different diameters in various places. But instead of pottery, you could actually do something else. How about if you photograph people? All right, so at this point, we're taking a brief intermission, and we'll continue. So thanks very much. Okay, so here we are again. Just to remind you, we ended up the previous session with peripheral portraits, and here is yet another one. This guy is pretty upset, I think. Here's a cute one. And a young lady standing on the turntable. I think you saw her that she was, as they introduced the topic. So now change the situation once more. And we're going to make the film move and the subject move and also pan or rotate the camera from side to side. Now, what happens then? Well, these are two examples. The braids on this girl's head are 180 degrees. The back of her head is not visible. So what she did is, as the camera moved from one side to the other, she made a 180-degree turn. Kind of mind-boggling, huh? And the guy did the same thing. And here's a cute one. Okay, so now we are again at a crossroads. So let's rotate the camera instead of rotating the subject. And then what happens? Well, there are people who have taken advantage of this, especially circuit panoramic camera users. These were made in early 1900s by Eastman Kodak, and they've been used worldwide to make panoramic photographs. On a more recent scale, in a commercial end, is the Alpha roto camera. Very expensive, very accurate though, very sophisticated. Here's a Halterama, which was a camera made here in the States. And all it is, as you look inside, is a way to transport film, and there's a slit in it. I mean, that's it. That's it for most of these cameras. Well, all of them, I'd say. A simpler camera that you could hold in your hand, and it would spin around, is the Globoscope. That was made here in New York City. There's some samples of photographs that could be made with this system. Here's a Globoscope panoramic camera image, and here's an Alpha panoramic image. And so getting back to this, rotating a strip camera results in panoramic photographs. And there is my improvised strip camera put on a rotating tripod head, and as it turns, it makes panoramic pictures. Now, I don't have one of those, but I do have this one. And here's one that some of you might know where it is. It's a courtyard in Toledo, Spain. Now, what if, gotta do it again. Now, what if if you wanted to make a really wide angle photograph? Well, in that case, you could put the camera on a tripod head, put a wide angle lens on it, so get good coverage up and down, and then you rotate the camera here in downtown Rochester, where I live. And then this photograph was hung from the ceiling in a hoop, and you could duck underneath the edge and be surrounded by the scene. And all the panoramic distortion that you would normally be associated with these pictures would kind of normally disappear, like it does in your brain or in your real self. Here's a simplified manually or motor driven camera that I made. It is fairly inexpensive to make. In this case, the drive mechanism consists of a connection to the inside of a cylindrical hole, and by way of a rubber roller, and that makes the sprockets pull the film through the camera. And as it moves through, you have a strip camera. With that crank on the left-hand side, you can make 360-degree photographs. But since you're rotating it by hand, you end up with your armpit in every photograph, as you can see here. And if you wanted to see that camera in motion, here it is. And here are a couple others from Santa Fe in New Mexico. And here's in a cave in the same place. So we've covered an awful lot of ground already, but we haven't talked about digital at all. So what about digital? Well, how do you improvise in digital? Well, first of all, you have to realize that the slit is nothing more than a vertically covering area, and a linear array can be found in most scanners. This happens to be a very cheap hand scanner. You draw this over a document, and it shows you a swath of the document, but then you do it a number of times, get it all together, and you can make larger scans. It's interesting to use this for panoramic cameras, as a strip camera, as a street camera. And there's the insides of the hand scanner. Now they're right to be covered up. And there's a slit inside of the camera. The scanner expects to move, and it does so by rollers that are attached at the bottom to transfer that motion to a slotted wheel. However, this scanner is not going to move anywhere. So how do you make the scanner think that it's moving? Well, I took that DC motor there, connected it with a rubber band to the shaft of this slotted disc, and that way, when it runs, the scanner thinks that it's rolling along. But what can you do with this? So I'll take a look at a number of examples on the use of street and strip cameras, both film and digital. You have to figure out which one is which. So here's a picture of that would be kind of difficult to make by hand. It shows the progression of ink as it rises on a blotting paper or paper tower with time. It shows you the acceleration of the ink as it rises, and then the deceleration with time. So getting a graph like this by doing it by hand or doing it with a motion picture camera is kind of difficult. This gives you an instant impression of time, and it's publishable. It can be referenced, etc. Now we'll take a look at another application. Here's a ping pong ball that's going to run down an inclined ramp. So the linear array inside of the camera is aligned with the sloping track. So I think I said it. The stroboscope provides timing marks. So we'll take that digital strip camera that I made and line it up that way. And there's the output on the screen on the left-hand side. But this is what, once it's downloaded, this is what the track looks like. As the ball starts to roll, it's slow, then it picks up speed. And then right underneath where it says time, if you go to the very bottom, there's a bounce effect. That's because the ball has reached the end of its travel and it's bouncing back. And if you were interested in how many times it bounces, you could do that. The strobe gives you timing marks every half a second there, and you include distance. You measure that at the subject, and out comes a graph that is very usable for describing the performance of a falling ping pong ball. And here's two ping pong balls at the right, and one of them hits first, it stabilizes, and then the next one hits it and bounces from the first one up, and it causes the first one to bounce as well. All right, so what else can we do? Well, we can make panoramic pictures, take that camera and rotate it. And here's the picture in my lab made with that system. So, but you'd think that this stuff was new. Well, sort of. Pictures of Mars were made with a scanning camera. This particular camera was extremely innovative because it was able to make images at a variety of wavelengths, and which is difficult to do for a standard camera. So this one was able to sample like 7 different wavelengths, but it did so not by scanning with a slit, but by scanning with a pixel. With every wavelength had a different pixel associated with it, and it was scanned over the scene. And as it is scanned, eventually each bit of information was transferred to digital and then sent to Earth in digital form, because analog would get distorted. Wonderful, wonderful, wonderful engineering accomplishment. So the first pictures from Mars were made with not only a slit camera, but from a pixel camera that was scanned over the scene. There was no reason to do it fast. Things were not moving, which is actually a problem, because if there were Martians there and they were moving around, that camera would be pretty hard pressed to image them. So then I wanted to make prints from my panoramic pictures. How do I do that? Well, I'll make myself a panoramic or a strip enlarger. I took a roller assembly from a Polaroid camera, installed that on the head of the enlarger. At the bottom, I used a paper transport developing device, and that moved the paper. Used a variable power supply to drive the film motor, and the slit was installed under the negative carrier. So this is kind of how it looked like. There was the paper being wound through. Since the paper was not sensitive to red, I was able to make the slit out of red filter material. And down on the bottom, you can see the film transport device that moves the film through the head. And then once you have this piece of paper exposed, then you develop it and you end up with a kind of a long picture. So, okay, what about digital? Polaroid. So what about Polaroid? Well, if you realize how the Polaroid pack is constructed, it moves the film past, once it's ready to be processed, exposed and processed. Once you get to process it, you have to pull it out of the pack. And it goes through a roller system which spreads the chemicals through the negative. Anyway, if you cover up the mask to begin with, so that nothing can go to the film, except you leave a fine slit at one end, then as you didn't expose it to begin with, but you open the shutter again and pull the film through as the film moves to the right to go around the corner, and then to the left to go through the processing rollers, it gets exposed in strip fashion mode. So I made this contraption that does that with a motor drive. The camera was really not modified a lot. The shutter was taken out. The lens cone was moved a bit, but that's about it. So then I took the camera and first at the bottom left, I pulled the paper negative out of the camera by hand, and then the next time I pulled the film with the electric motor, and you can see that the electric motor drive is smoother, but the other one shows promise of what could be done if you pull the film in a more even way. So then you can play games with this camera. And a friend of mine used it to photograph the students all over the place. Now coming up is a forensic application, which is maybe a more serious application instead of distorted people. And for this, you take the digital strip camera, you put it, you aim it so the slit is aimed at the center rotation of a bullet, and you can let the bullet rotate and let the scan over time, and you end up with a picture of the bullet like this. And you might remember the cylinder, the piston that we used earlier, and that in digital form looks like that. But of course, just as we did before, instead of industrial work, we could do artistic work. And here's one of those, and another one. But you don't have to have a slit inside of the camera. You can also have it outside. In that case, there's this box here. In the front, there's a slit. The camera is looking through the box, through the slot, And in order to make a photograph with a standard camera, you just rotate it, and with the shutter open. So as the shutter is open, the camera is panned. At the beginning, it sees one side of the box. Later on, it sees the other side of the box. In the meantime, it has seen the subject over a period of time. And a different, here you can see the combination of the two. That comes out of it with a slit, just a slit in front of the camera. And you could either have it in a box or you could just have it open. As long as you don't put light on the backside. But these are some of my students who had a blast, as they say. They had a lot of fun with this photograph. Then once I had an opportunity to make a consulting job to make peripheral or rollout photographs to make decals for a pottery company. So they presented me with these objects. Now, there was no problem dealing with the cylindrical ones. You just put them on a turntable, you aim the camera at the center rotation of the pot, and voila, you make a 360-degree picture of the cylinder. Now, the next thing is a little bit more complicated. Here we have the teapot. The teapot is not cylindrical, it's conical. So what happens, what if you want to make a peripheral photograph of this? Well, if you match the speed of the image for the base, you would not match the speed of the image at the top, and vice versa. So you have to find a system where the film moves faster in one place than the other. And with regular film, that's impossible. However, if you realize that you need an image to move faster at one place, or the film move faster at one place than another, you make yourself a camera that starts based like this. The film is on a disc, and it's attached to the disc holder, and it has a motor in the back, and they can turn. So if you place the base of that cone towards the edge of that circle, when the circle turns, the center will turn slower than the edges. And you can, with slight adjustments, you can match the correct speed of rotation with the location of the subject. This is what the camera looks like. And there is essentially it's a box, there's a turntable, and a DC gearhead motor, and so on. But I think you get the gist of the idea. So here's the camera in photographic detail. The slit in the camera is not visible, I guess, in this photograph, but trust me, there is one. It's a radial slit. And now if you take this camera and you aim it at the teapot, and you have made the proper adjustments in terms of inclination and among where the base is going to be located, etc., you end up with images that negatives would look like on the top left. The negatives also, again, one of the positives of that are at the bottom. And then when you match the cone that you generated photographically, you notice that there is a pretty good correlation between the two. And the manufacturer was quite happy with this. I'm not sure, I might have interfered in copyright laws for doing this for them, but anyway, it's an application that I have not seen anywhere else. But again, instead of making industrial things, you can do artistic things. So here's a bouquet of flowers rotating on a turntable, and here's a figure rotating on a turntable. Now, when a film camera like that is tilted upwards, in that case, the horizon moves faster than the apex, and this camera can compensate for that and make panoramic records like this and like this and so on and more. And you might recognize this location. And of course, we can have fun. We can do all kinds of things with this, fun type things. You can let your imagination run rampant. So bye-bye. Thank you. Köszönöm szépen. I hope to maybe hear from you. My email address is shown here, as is my web address. I also have a site on Facebook if you want to contact me that way if you want to. Okay, so I guess that's the end of my presentation. Thank you very much for your time, for your patience, and be well, you all.